Hello. Can you hear me?
Yes,
Uh, yeah. Can you see the screen also?
yes, I can.
Okay, so we'll just wait for 5 minutes if
Right.
someone else is joining, and then we'll get started.
Yeah, sure,
Yeah.
sir, sure.
Yeah. Uh, Hi everyone. Uh, we'll get started today. Uh, I'm Arpit. I'm your TA for this course, Introduction to Biostatistics. And today is our fourth live session where we'll be discussing practice questions based on lectures of week 4. Uh, yeah. Before we get started, here are some important links. So the link for the live session, then the link for the YouTube channel where all the recordings of the live sessions are being updated. So if you have missed any of the classes before, you can go to this channel and check them out. And the link to the Google Drive where all the PPTs for the live sessions and any R code. So some of the sessions have R code that has been uploaded. So we'll get started with practice assignment 4. Before that, does anyone have any questions or doubts regarding last week's lectures or maybe something that was taught this week?
No, sir, not right now.
Okay, great. So we'll get started with practice assignment 4. So the first question is, so in this week we were taught about mostly conditional probability, permutation combinations, and I think a little bit about variance and covariance towards the end. So yeah, most of the questions are from probability and some of them are from like distributions. And next week we'll, I think, delve deeper into these probability distributions and stuff. So yeah, the first question is, if 3 items are taken out randomly from a bag containing 10 distinct items, what are the different combinations of items that are possible? So we have basically n is basically the total number of items, which is 10 distinct items, and r is basically the number of items that we have to choose, which is 3. So since there are 10 distinct items and we are randomly taking out 3, and we don't care about the ordering of it because we are talking about combinations here. So to figure out this number, we'll use the formula NCR, uh, which is basically n factorial by r factorial into n minus r factorial. So in our case, n is 10 and r is 3. So we'll just substitute those values. So it's 10 factorial divided by 3 factorial into 10 minus 3, which is 7 factorial. So if we write it out, like expand this, so it will be 10 into 9 into 8 into 7 factorial divided by 3 into 2 into 7 factorial. So this will cancel out. 2 we can cancel out here. 3 we can cancel out here. So what we have is 10 into 3 into 4. So 12 into 10, which is 120. So the answer here will be option A, 120. Okay. The next question is, in how many ways can you arrange the letters in the word stats? Right. So if we are in general, like when we have problems like this, if we are talking about, let's say, arranging a few letters. So for example, let's say we have A, B, C, D, E, and we want to figure out how many uh, different ways can we arrange these letters. So when we are arranging, we'll generally form like 5-letter words because there are 5 letters. So we have basically 5 blanks that we can fill up. So the first blank can be any of these letters. So A, B, C, D, or E. So this has 5 possible values. But once we take one of these letters, so let's say we put A here, then for the second choice, we just are left with these 4 letters, right? So here we have 4 uh, basically options available to us. Then after we choose another one, let's say we choose C, in the next one, we have 3 options available to us and so on. So the number of ways you can rearrange all these 5 letters will be 5 into 4 into 3 into 2 into 1. which will turn out to be, I think, 120 in this case, like 5 factorial. That's what we'll write. Now, in cases where we have repetitions of letters, so for example, let's say we have A, B, C, D, and we are asked how many ways can you arrange this, right? So for convenience, we'll treat these two A's as different letters. So let's say A1 and A2 are two different letters. So if we follow this logic of the one I explained here, again, we can have basically 5 different letters here, 4 here, 3, 2, 1. So again, it will be 5 factorial because we are multiplying all of these. But now the thing is that since this letter A is repeated, so when we are, so if in these 5 factorial combinations, we might have places where basically we have A1, A2, B, C, D, then we have A2, A1, B, C, D, right? Or we might have A1, B, C, D, A2, and A2, B, C, D, A1, right? Now, for our convenience, we have just denoted them as two different letters, but actually both of them are A, right? So this word and this word are basically the same thing. So when we have these kinds of repetitions, some of our what do you say combinations will basically collapse into the same word. So in this case, since A is repeated twice, there are basically 2 factorial ways in which we can arrange. So basically, we can have A1 and followed by A2, or we can have A2 followed by A1. So if we have two A's anywhere, so the first one can be A1 or the first one can be A2. So there are always two cases. So what we need to do here is, in this case, if we need to find out the number of unique combinations, it will be 5 factorial divided by 2 factorial. 5 factorial is for all the letters that we have, 5 letters we have. 2 factorial because A is repeated twice. So if A is repeated 3 times, there will be A1, A2, A3, and we'll have 3 factorial ways of arranging that, right? So in that case, we'll do 5 factorial divided by 3 factorial. And if multiple letters are repeated, so for example, we have A, B, B, C, and we want to figure out how many ways we can, distinct ways we can combine these to form 5 lettered words. Uh, so we'll have 5 factorial divided by 2 factorial into 2 factorial. One of them is because there are two A's, and one of them is because there are two B's. Great. Is that clear? Yeah.
Yes, sir.
So, yeah, using this, thanks. So using this formula, here we have, again, we have 5 letters. So STATS, and here two of the letters are repeated. So S is repeated twice and T is repeated twice. Right, so here the number of ways we can arrange these letters would again be 5 factorial divided by 2 factorial into 2 factorial, which turns out to be 5 into 4 into 3 into 2 into 1 divided by 2 into 2. So it's 5 into 3 into 2. So 6 into 5, which is 30. So the answer here will be option D, that is 30. Okay. So the next question is 60% of individuals in a residential complex love dogs and 40% of them love cats. 30% of individuals love both cats and dogs. So what is the probability that a randomly selected individual loves cats given that they love dogs? So in this case, we are going to use something called conditional probability. So basically, we are given like, we'll just write down first what all we are given. So PD is basically probability of someone loving dogs, right? So probability of an individual loving dogs in the residential complex, so which is given to us as 60% or which will be equal to 0.6. Then PC is basically number of people that love cats. again, that is given as 40%, which is equal to 0.4. Then we have 30% of individual loves both cats and dogs. So probability of someone loving cats and dogs, or probability of C intersection D here will be 30%, which is 0.3. So we are asked, what is the probability that a randomly selected individual loves cats given that they love dogs? So we are now trying to find the probability that someone loves cats given that they love dogs. So this is basically the way in which we write down conditional probability. So probability that event A happens given that event B has already happened. And this is basically given as probability of both events happening divided by the probability of the second event happening. So in our case, it will be probability of uh, the individual loving both cats and dogs divided by probability of the individual loving dogs, right? So if we basically make a Venn diagram here, might illustrate us better. So we have C, we have D. So these are the people in C are the people who love cats, in D are the people who love dogs. And in the intersection area are the people who love both cats and dogs, right? So what we are uh, asked is, we are basically asked, what is the probability that someone loves cats given that they love dogs? So we know that this event has already happened. So we know that the person loves dogs. Now we want to know what is the probability that the person also loves cats. So that will be basically this area divided by the whole thing, like the whole area for D. So that is basically what we have written here, that given that the person loves dogs, what is the probability that they love cats is basically probability of them loving both cats and dogs divided by probability of them loving dogs. Right. So we have all the values. We have probability of C and D is 0.3 and probability of D is 0.6. And that basically turns out to be 1 by 2 or 0.5. So the answer here is option B, 0.5. Right. So we can also, so this probability of C intersection D can also be written as probability of CD, or it can also be denoted as probability of C and D. Right. So these are just the different ways in which we write this. Now, the next question is, a student tosses two fair die. What is the probability that they will both land on an even number? And the second part is, what is the probability that the second die will land on an even number if the first one has already landed on an even number? Right. Here again, we are basically asked to calculate two probabilities. So a student is basically tossing two dice. So the outcome of that for die one can be 1, 2, 3, 4, 5, 6. And for die 2 can also be again 3. One, and just write it down. So the probability for so the die 2 can also be 1, 2, 3, 4, 5, 6. One of these numbers will get right. So the probability that die 1 is even is basically 3 by 6, because we have three even numbers and in total we have six numbers. So it's 3 by 6, which is 1 by 2. Similarly, probability that die 2 is even. So these are separate events. So die 1 is even, and die 2 gives us even. So these are two separate events we are calculating. Again, the probability here, since there are three even numbers, it will be 3 by 6, which is 1 by 2. Right. Now we are asked, in the first question, we are asked, what is the probability they will both land on an even number? Right. So in the first case, what we are asked is, what is the probability that die 1 is even and die 2 is even? Right. Now, since we know that uh, whatever number comes out in die 1 does not affect whatever number comes out in die 2, right? Because they are two independent events. Because they are two fair dice, right? So if you are rolling a 4 on dice 1, it does not it does not basically increase your chances of getting a 4 or any other number in die 2, right? So the chances of getting any even number in die 2 remains the same. So since we know that these two are independent events, we can say that the probability of both the events happening is basically multiplicative. So this will be equal to probability that die 1 is even into probability that die 2 is even. And that is basically 1 by 2 into 1 by 2, which is 1 by 4. Right. So for the first part, our answer is 1 by 4. Now the second question is, so if you're in a hurry and if you basically make that calculation in your exam and you see that only one of these options has it might be okay. We'll come to that. Yeah. Anyways, we'll calculate. So the second one is, what is the probability that the second die will land on an even number if the first die has already landed on an even number? So now we are in the second case. We are seeing what is the probability that uh, second die will land on an even number if first die has already landed. So die 2 is even, given that die 1 is even. Right. So again, we'll use the formula for conditional probability here, which is basically that probability that die 2 is even and die 1 is even divided by probability that die 1 is even. Right. So this we just calculated. So we know that probability of A and B happening is the same as probability of B and A happening. So basically these two probabilities, this one and this one, are the same. So it will be 1 by 4 divided by probability that dice 1 is even, which is 1 by 2, which turns out to be 1 by 2. Right. So our second half, the answer is 1 by 2. So the answer here should be option D, but it's jumbled. Right. So yeah, it should be 1 by 4, comma 1 by 2. First part, this was the second part. Okay.
Yes, sir.
Yeah. Question number 5. According to the weather forecast, there is a 50% chance of rain. There is a 40% chance that you may have to step outside for your house to fetch groceries. If the probability of it raining and you having to step outside is 30%, what is the probability that you will need to step outside when it is already raining? So again, this looks like a conditional probability thing because again, like if the probability that this is happening is given, what is the probability that another thing will happen? Right. So we'll just write out uh, in short forms whatever is given. So there is a 50% chance of rain. So basically probability that it will rain is 50% or 0.5. There is a 40% chance that you may have to step outside to fetch groceries. So probability of stepping out is 40% or 0.4. If the probability of it raining and you having to step outside is 30%, so the probability of basically rain and stepping outside is 30% or 0.3. What is the probability that you will need to step outside when it is already raining? So what we have to calculate is probability that you have to step outside given that it is already raining. So again, this is a direct formula. So what we have is probability that you are stepping outside and it is raining divided by probability that it is raining. So this is 0.3 divided by 0.5, which is 3 by 5. So the answer here would be option C, 3 by 5. Okay. Number 6, a box contains 3 red, 2 blue, and 5 yellow marbles. If one marble is drawn at random, what is the probability that it is not blue? So inside the box, we have 3 red, we have 2 blue, and we have 5 yellow. Right. So we are randomly drawing a marble. So the number of, what do you say? Uh, so the total number of marbles is basically 10, right? So that will be our denominator for any probability that we calculate here. So probability that it is not blue will be number of instances when the number of instances or number of cases where the marble is not blue divided by total number of marbles. So number of cases in the marble is when the marble is not blue is 3 plus 5, which is 8. And total number is 10. So it's 8 by 10, which turns out to be 4 by 5. So option C. The next question is, which of the following can be represented by a discrete random variable? A, the number of sweets eaten in a sitting. B, the distance between home and workplace. C, the speed of a race car. And D, the weights of students in a classroom. So when we talk about discrete random variables, we know that discrete random variables are variables which can take on discrete values. So for example, when you roll a die, the number that comes up, if you treat it as a score, if you treat it as a random variable, then that is a discrete random variables because that can only have values which are discrete and limited. So it can have values ranging from 1, 2, 3, 4, 5, 6. Again, like if you are talking about, let's say, rolling 2 dice and you are seeing what is the sum of the numbers that come up on the dice. If you are treating that as a, so basically sum of 2 die. If you're basically looking at that, that is again a discrete random variable because those values can range from 2 to 12. Right? If you have 1, 1 in both the dice, you'll have 2. If you have 6, 6 in both the dice, you'll have 12. And every other number, for example, 3, 4 is 7, 5, 5 is 10, 2, 2 is 4. All of them come somewhere in between, right? But they are again discrete values. So it can be from 2, 3, 4, 5 till 12. Right? Whereas if you're talking about continuous random variables, for example, let's say we're talking about a random variable A, which is the uh, height of students in a class, then that can take any value from a continuous distribution. So the height can be, let's say, 171.6 centimeters. It can also be 172 centimeters. It can be 172.3. It can be 150.1, right? And it can also be 150.15. Right? So it can take on multiple different value. It can take up values from a continuous range, right? So that's why it's a continuous random variable. And in the case of a discrete random variable, we have defined values that the random variable can take. So if we going from the height to the weight, we can see that weight is again similar. So weight is a continuous random variable because we can have values of weight which are, let's say, 75.6, 75.65, 75.62, and so on and so forth, right? Speed of a race car is again a continuous variable because speeds also can have continuously varying ranges. So if you start a car, you're starting it at zero, but when you reach 50, you have essentially gone through a lot of different numbers and not basically jumping from discrete steps. Like you're not going from 0 to 10 kilometers per hour, then 20. You're not making those jumps. You're smoothly going along all of them, right? So it's a continuous variable. Again, the distance between home and workplace will again be a continuous variable because it can take values in a wide range, like which can be positive real numbers, right? But the number of sweets eaten in a sitting is a discrete random variable because you can either eat, basically, if you're tracking the number of sweets eaten, we are basically tracking if there's one, two, three, four. So it's in discrete steps. So you cannot have, let's say, 1.1 sweets eaten, 1.05 sweets eaten, where it doesn't make a lot of sense. Right. So the answer here will be option A, number of sweets eaten in a setting. Question number 8 is on rolling two fair dice, we obtain two independent random variables, x and y. Calculate the probability that x is greater than 2 given that y is equal to 3. Right. So again, we are rolling two fair dice. X is our random variable for the first die, which can, it's a discrete random variable as we talked about. It can again take on values from 1 to 6. And y is for the second die. First dice, second dice. You can take 1, 2, 3, 4, 5, 6. Right. So we are asked what is the probability that x is greater than 2 given that y is equal to 3. Right. So again, uh, because there are two dice and there are two independent random variables, we know that the role of one die won't affect the role of the other. And basically, these two are independent. So the probability of x is independent of the probability of y, right? So what we can say here is probability that x is greater than 2 given that y is equal to 3 will be the same as probability that x is greater than 2 because they are independent events. So the probability of one does not affect the probability of the other. Right. So in this case, we have to calculate what is the probability that x is greater than 2. So that will be probability that x is equal to 3 plus probability that x is equal to 4 plus probability that x is equal to 5 plus probability that x is equal to 6. Right. So each of these are basically one number out of 6. So this is 1 by 6. Probability of getting a 4 is again 1 by 6. For 5, it's 1 by 6. And for 6 is again 1 by 6. It's basically 4 by 6, which turns out to be 2 by 3. The answer here will be option B, 2 by 3. Right. Next question is, 3 cards are dealt from a well-shuffled deck. What is the probability that among the cards dealt, there is exactly one king? Right. So we have said that we are given 3 cards from a shuffled deck of cards. So a shuffled deck of cards will have 52 cards. So our N here is 52. And our basically R here is 3 because we are choosing 3 out of 52. So if we look at all the combinations that we can get here, it will be basically yeah, all the combinations will basically be NCR again. So all the combinations of 3 cards that we can take from these 52 cards. So that will be basically 52 C3, which is divided by 3 factorial into 52 minus 3, which is 49 factorial. Right. So that is without any constraints. We are not thinking about the kings and all of that. But now, so this is the total possible combinations when we have 52 cards and we are taking 3. Right. Now, what we are given is the constraint that there is exactly one king. Right. So let's say, so we have to find the probability that in these 3 cards, there is exactly one king. So that probability will basically be one king on 3 cards. It will basically be the number of combinations with exactly one king divided by the total number of combinations. Right. So we have the total number of combinations, which is 52C3. Right. Now we need to figure out what are the combinations in which exactly one king is present. So one easy way to do that is to basically denote this card as a king. Right. Now let's say in all of the hands, in all of the cases, since we are looking at combinations where there's exactly one king, in all of the cases, one of the cards is a king. So what we are actually left with is a choice for these two. So these two can be anything other than kings, right? And this king, again, this king card can be any of the from any of the suits, right? It can be a spade, it can be a hearts, it can be a what do you say, club, or it can be a diamond, right? So we have 4 possible values that can come here, right? So this, yeah. So basically, this will have 4 possible values that can happen here. And then we have to see what further as 2, how many combinations we can get. So this is simple. Now, in this case, our n dash will basically be n minus 4, since we are removing all the king cards because we don't want any more kings here, right? So we'll be choosing from cards which are not king. Doesn't matter what suit of king we have here, but these cards cannot be king. So our n prime will be n minus 4, and our r prime is basically r minus 1, since we have from 3 gone to 2. So this is basically 2, this is basically 48. Right. So, so this basically translates into a problem of choosing 2 cards from 48 cards in total. discarding the kings, right? So that is the total number of combinations in which this two cards can be chosen. And that we then need to multiply with the first thing that we had, which is 4. So the, what do you say? So basically this will be 48C2. So there are 48C2 different ways of choosing these combinations. And then this combination can then again be mapped with a king from either of these 4 suits. So this is again multiplied by 4. So there's a total number of combinations in which we'll have exactly one king, right? So number of combinations with exactly one king. Okay. So now we'll just substitute these values that we got here into this. So probability of one king in 3 cards is basically 4 into 48C2 divided by 52C3, which is equal to 4 into 40 factorial divided by 2 factorial into 46 factorial. So 48 minus 2, right? Into. So we'll just flip this. We'll put the 52 factorial down. And on top we have 3 factorial and 49 factorial. Right. So this 48 factorial, we can basically, when we expand this 52, we can basically, actually we'll just leave the 42 to be. So if we, we'll just expand this. So we have 4 into 48 into 47 into 46 factorial. Sorry. Into 3 into 2 into 49 factorial divided by 2 into 46 factorial into 52 into 51 into 50 into 49 factorial. So this will cancel out, this will cancel out, this will cancel out. Then what we have is 4 into 48 into 47 into 3 divided by 52 into 51 into 50. So we use a calculator. 4 into 48 into 47 into 3 is 27,072 divided by 132,600. Now this turns out to be 0.204, so approximately 0.2. Okay, so we have here 0.2, so the answer here will be 0.2. Was that clear? Did everyone understand why the 0.2 and how we calculated all these combinations? Okay, I'll just go over it once more, just to be clear, because these kinds of questions you might get and might be slightly more tricky to figure out. So the total number of combinations is easy to understand. We have basically 52 cards. Out of this, we are choosing 3 cards. So it's straightforward 52C3. Then here, since we are fixing one of the cards as a king, and here the ordering does not matter, so we'll fix the first card as the king. So what we are left with is 2 cards, and those 2 cards can be anything other than kings, right? So here, for these 2 cards, what we have is 48C2, because if you take out 4 kings from the 52 cards, we are left with 48. And there are 2 cards that we need to choose. So 48C2, that will give us all possible combinations of these 2 cards. Then that will again be multiplied by 4, because we have 4 king cards. So 4 cards of king in each of the suits. So it can be either a spades, a heart, or a club, or a diamond. Right. So it's 4 into 48C2 divided by the total number of possible combinations, which is 52C3. Right. Now the next question is, assume a random discrete variable x such that 0 is less than equal to x less than equal to 3. Find the value of a given that probability x equal to 0 is 1 by 9, probability x equal to 1, 2, and 3 we are given. Right. So we have a random discrete variable x, which falls between 0 to 3. Right. So our x falls between 0 to 3. Right. Now, what we know that is for any random variable or any kind of probability calculation, the sum of all the probabilities should equal 1. Right. So in this case, the sum of basically probability of x equal to n, where n is equal to 0 to 3, since x can vary from 0 to 3, right? So this summation should always be equal to 1, because we are talking about a probability here, right? So we'll just write this equation down. So the summation is basically probability that x equal to 0 plus probability that x equal to 1 plus probability that x equal to 2 plus probability that x equal to 3 is equal to 1. Now we'll just plug in the values. X equal to 0 is 1 by 9, 4 by 9 is 1 by 9 plus 4 by 9 plus A and 3A. A plus 3A is equal to 1. So if we add this, we get 5 by 9 plus 4A is equal to 1. If we take 5 by 9 to the other side, we have 4A is equal to 1 minus 5 by 9. So 4A is equal to 4 by 9. So this will be 9 minus 5, which is 4 by 9. And if this 4 cancels out, so we have A is equal to 1 by 9. Right. The answer here will be option A, which is 1 by 9. Right. So we have another question where we are asked how many ways can the letters of the word biostat be arranged. So here we have 7 distinct letters. So our numerator will anyways have 7 factorial. Now we'll see if there are any letters that are repeated. Here there are basically 2 T's and nothing else is repeated. So it will be 7 factorial by 2 factorial. So that is option B. Okay. Question number 12. Uh, From a group of 8 men and 5 women, how many ways can a committee of 4 people be chosen such that exactly 2 of them are women? Right. So we are given a total of 13 people, out of which 8 of them are men and 5 of them are women. And we are asked to form a committee of 4 people. Right. So, yeah, we are choosing 4 people. And we are asked, how many ways can the committee be chosen such that exactly 2 of them are women, right? So we have 4 people. Now, what we need to do here is basically, since there are a total of 5 women, we can choose and we need to find out committees where there are exactly 2 women, right? So we can basically choose 2 women out of these 5 women, right? So that we can choose, that is like that will be our 2 women on the committee, and we need to have 2 men on the committee also, right? Because there are 4 people. So this will again be multiplied by 8C2 because there are 8 men and we are choosing 2 men, right? So this basically divides out into 2 combinations. We have 5 women, out of which we are choosing 2 women for the committee, and we have 8 men, out of which we are choosing 2 men for the committee. And the total number of combinations will be the multiplication of this, because any of these women can be paired of, like any of these chosen pairs of women can be paired up with any of these chosen pairs of men, right? So this turns out to be 5 factorial by 2 factorial into 3 factorial into 8 factorial by 2 factorial into 8 minus 2, which is 6 factorial, right? So we have 5 factorial into 8 into 7 into 6, 5 into 4 into 2, 6 into 5 factorial. So this cancels out. This cancels out. This. And these two will cancel out the first. So what we have left is 8 into 7 into 5, which is 46 into 5, which is 280. So the answer here will be option B, 280. Right. Next question is, a fair coin is tossed 3 times. What is the probability of getting at least 2 heads? Right. So if we toss a fair coin 3 times, we'll have 8 outcomes because we're tossing it 3 times. Here there are 2 outcomes. It can either be a head or a tail. Here it can be a head or a tail. Here again it can be a head or a tail. So we'll have a total of 8 outcomes. We'll just write out all the outcomes because it's easier to do it that way. So we can have heads, 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 tail, head, tail, head, head, tail, 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 and then again tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. So this is our sample space. These are all the combinations. Now we'll just count out the combinations in which we are getting at least 2 heads. So we are getting 3 here, 2 here, 2 here, 2 here. We have 4 cases. Probability of getting at least 2 heads is equal to 4 divided by the total number, which is 8, which is 1 by 2. The answer here is option C, 1 by 2. Wait. Question 14. So a bag contains 4 red balls and 6 green balls. 2 balls are drawn at random without uh, replacement. What is the probability that both the balls are red? Right. So total, basically total number of balls is equal to 6 plus 4, which is 10. two balls are drawn without replacement. So we are not replacing them once we are picking them out, right? So what is the probability that both of them are red? So we are basically picking out two balls, right? So when we are picking out the first ball, what is the probability that it is the first ball is red? It will be 4 divided by 10 because we have 4 red balls out of total. So 4 red and 6 green, right? 4 red balls out of a total of 10. But when we are picking so this is for the first ball. When we are picking the second ball, we are not replacing. So without replacement means basically we have not, what do you say? Just a second. Yeah. So without replacement basically means that we have not replaced the balls that we have taken up. Right. So the red ball that we picked on the first time, this ball is already out of the game. So now we have a total of 9 balls because one of them is gone. And out of we have total of 9 balls for the second attempt. Total is 9. Out of the 9, 6 will again be green because no green ball was taken out, and 3 will be red. Right. So the probability of getting a red ball on the second turn is 3 by 9. Right. So the probability that both of them are red will be probability of first ball being red multiplied by the probability of second ball being red. So it will be 4 by 10 into 3 by 9, which is 5, 2, 3. It's 2 by 5 into 3, which is 2 by 15. Answer here is option B, 2 by 15. Right. Does anyone have any questions or doubts till now? Okay. The next question is the probability that a student passes biology is 0.7, chemistry is 0.6, and passes both is 0.5. So what is the probability that the student passes biology given they have passed chemistry? Right. Again, this is a conditional probability. So we have the probability that the student passes biology is 0.7. We have the probability that the student passes chemistry, which is 0.6. We have the probability that the student passes both probability and biology and chemistry, which is basically 0.5. Right. So what we are asked to find is what is the probability that the student passes biology given that they have passed chemistry. Right. So this is again using Bayes theorem, Bayes formula. We have probability of B and C divided by probability of C, which is 0.5 divided by 0.6, which is 5 by 6. Answer here is option A, 5 by 6. Right. Question number 16. So how many different 3-digit numbers can be formed using the digits 2, 4, 6, 8, and 9 if repetition is not allowed? So we are trying to form a 3-digit number here, right? So we have 3 blanks to fill. We are given 5 digits, 2, 4, 6, 8, and 9, and the repetition is not allowed. So once one digit is used, it cannot be used again, right? So for the first digit, it can be either 2, 4, 6, 8, or 9, right? So we have 5 choices here. But once we have chosen this, for example, let's say we chose a 4. In the second case, we are left with 2, 6, 8, and 9. We are left with only 4 options. So we have 4 options here. Again, if we make a choice here, let's say we choose 8 in this case, we'll have 8, 3 choices for the third option. Let's say we choose a 2, it doesn't matter. So we have 3 choices here, right? So the number of different 3-digit numbers that we can form is basically a multiplication of all these choices that we have. Is basically 5 into 4 into 3, which is 12 into 5, 8, 5 into 4, 20, 20 into 3, 60. Yeah, 12 into 5, 60. So the answer here is option A, which is 60. Great. Now, if we were asked that how many different 3-digit numbers can you make using these digits, and repetition is allowed. So if the not was not here, then what we'll have is we have 3 blanks. And since repetition is allowed, this can be 2, 4, 6, 8, 9, one of these 3. So we have 5 options here. This can again be 2, 4, 6, 8, 9, because we can repeat the digit that we chose here. We can have 4, 4, 2, 2. So this again will have 5 options. And the third one again will have 5 options, 2, 4, 6, 8, 9. Right. So in this case, we'll have around 125 options because we are allowed to repeat the digits. Right. But without repetition, it's 60. Next question is, which of the following is a property of a discrete probability distribution? Option A, all probabilities are positive but may sum to less than 1. This is incorrect because the sum of all probabilities should be 1, which brings us to option 2, which is correct in this case. Option C, probabilities can be negative for their events. That is false because one of the axioms of probability is that probability of any event E lies between 0 to 1. Right. So probabilities cannot be negative because when we are talking about probability, we are talking about the chance of something happening. Right. And there's never a negative chance of something happening. It's either 0 or there's a positive chance of something happening. Right? A negative chance of something happening doesn't make sense mathematically. Right? All outcomes must be equally likely. This is incorrect because we can have discrete probability. So most of the discrete probability distribution that we uh, like discrete probability examples that we talked about, for example, tossing a coin or say, uh, rolling a dice, uh, have all outcomes which are equally likely. But if we are talking about, let's say, a loaded die or a biased coin, then the outcomes are not equally likely. Right? So or if we have a discrete probability distribution like this, we have 3 values that x can take 0, 1, or 2, and probability of it's basically half here, 1 by 4 here, 1 by 4 here. In this case, all the outcomes are not equally likely. So like a discrete probability distribution does not need to have equally likely outcomes, right? But the only option here that is true, which is a property, is basically option B. The sum of all the probabilities should be exactly equal to 1, right? Question number 18. 2 dice are rolled. What is the probability that the sum is 9 given that the first die shows a 3? Right. So there are uh, 2 ways we can do this. One way would be to invoke conditional probability. So for example, probability that, uh, let's say we are treating the 2 dice as 2 random variables, x and y, right? So what is the probability that the sum is 9? Probability that sum is equal to 9 given that x is equal to 3. So that can be probability. So this is a conditional probability, and this will be basically some probability that sum is equal to 9 and x equal to 3 divided by probability that x equal to 3. Right. So we can basically make these calculations that so we can basically make these calculations and arrive at the value. Otherwise, the other way to go about it is basically, since it's 2 dice and we know what 1 dice is, so we'll just have 6 options, right? So the first dice is has rolled a 3. So the second one can be a 1, it can be a 2, it can be a 3, it can be a 4, 5, or 6. Right. Now the sum here is 4, it's 5, 7, 8, and 9. So in one of these cases, we have the sum of 9, and in total, we have 6 cases. So this is basically fixed. It does not matter, right? So the probability that the sum is 9, given that x equal to 3, is basically number of cases in which the sum is 9, in this case, which is 1, divided by total number of cases when x equal to 3, which is 6. So it's 1 by 6. Doesn't matter. Same. So the answer here will be option A, 1 by 6. Question number 19. The probability mass function of x is given by Px equal to x is equal to x by 10 for x equal to 1, 2, 3, 4. What is Px is less than equal to 2? Right. So we are given that the probability mass function Tx equal to x equal to x by 10, right? Or x equal to 1, 2, 3, 4. So we are asked what is probability that x is less than equal to 2. This is nothing but probability that since x can be 1, 2, 3, 4, there's basically probability that x equal to 1 and plus the probability that x equal to 2. Right. So when x equal to 1, the probability of x equal to 1 is basically 1 by 10. We just substitute the value x as 1, 2, 3, 4 here. Then we have probability x equal to 2 is 2 by 10. So 2 plus 1, 3 by 10, which is 0.3. Answer here is option B, 0.3. Right. Now, question number 20. The probability distribution function of a continuous random variable is given below. Calculate the value of C. Right. So just write it out. So the probability distribution function f of x is given as C into 3x squared minus x when x is between 1 and 4. Right. Otherwise, 0. Right. So we know that the integral of the probability distribution function for continuous random variable is 1. Right. So we'll use that property here. So what we know is if we take the integral from minus infinity to infinity f of x dx, this is equal to 1, we know. Right. Now, since we have anything that is basically when x is less than 1, right, it's 0. When x is greater than 4, it's 0. So what we can do is we can divide this interval into 3 intervals, one going from minus infinity to 1, f of x dx, plus 1 to 4, f of x dx, plus 4 to infinity, plus infinity, f of x dx. Equal to 1, right? Now we know that f of x here will be 0 because x is less than 1 here, right? F of x here in the third term will again be 0 because x is greater than 4 here. So what we are left with is only the inner integration. So what we have here is integral 1 to 4 f of x dx is equal to 1. That implies we'll substitute f of x in this range, which is c into 3x square minus x. We can take the constant outside. So what we'll have here is basically here. That implies so integral of 3x square, uh, basically integral of 3x square will be equal to 3x cubed by 3. So it's n plus 1 divided by n plus 1. So this will cancel out. It will be x cubed. And the integral of minus x will be minus x squared by 2. Right. So what we'll have here is basically x cubed minus x squared by 2 in the limit 1 to 4. So c into this is equal to 1. So we'll just substitute these values here. So c into 4q minus 4 squared by 2 minus 1q minus 1 squared by 2 equal to 1. So c into 4 cube is 64 minus 4 square is 16 by 2, 8 minus 1 minus 1 square is 1, 1 by 2 is 0 0.5. Sixty-four minus 8 is 76, minus 1 is 70. Yes, 64 minus 8 is 76, minus 1 is 75, 74.5. Mm, 0.5 is 0.5. Oh, sorry, no, 76, no, sorry, 56. It was 56 minus 1 is 55. Okay. 1 minus 0.5 is 0.5. This is basically 56. So 56 minus 0.5 is 55.5. C into 55.5 is equal to 1. That implies C equals to 1 by 55.5, which is 10 by 555, which is 2 by 111. The answer here is option A, which is 2 by 111. Right. So when you have questions like this, what you need to do is you need to basically, or questions like this, which are very similar, what you need to do is basically, we need to remember that the sum of the probability mass function across all values for discrete random variables will be 1. And actually not this question, but like if you have a similar like discrete case, maybe if you have a question like that, you can do that sum of all the I think we had one question like that where we had to find a, is it not? This one, right? So in this case, the sum of all the discrete probabilities should be equal to 1, right? That's what we basically use to get at the value of A. And again, in the last question, what we have is like we have a continuous random variable whose probability distribution function is given. And we know that the integral in this case of the probability distribution function should be equal to 1. So that is what we evaluated. And we came out to this answer where C is equal to 2 by 111. Right. So, does anyone have any questions or doubts regarding any of the questions that we discussed today? Okay, question number 20. So, in question number 20, what we are uh, asked is basically that the probability distribution function of a continuous random variable is given, right? So, probability distribution function. So, for a continuous variable x, let's say continuous random variable, we have a probability distribution function, which basically tells us what is the probability of the value of x approaching a certain value, right? So this is a probability, and this is basically different values of x. So for example, if you take uh, a class in which you measure the heights of 100 people, like different students. So your x-axis here might be the height, and here you might have the probability or the frequency of, yeah, the probability distribution of basically getting that height. So the relative frequency of getting that height in some sense. So for continuous functions, we have a continuous variable like that, which is called the probability distribution function. It basically tells us, what do you say, how the um, probability of different values change, right, as we go along the axis. For discrete functions, we'll have probability mass functions, which basically happens in steps, right? So we have a distinct probability for each of the discrete random variables that we have. In the case of a discrete random variable, each of the discrete values that we have in case of a discrete random variables But in the case of continuous random variable, what we have is a probability distribution function, which is something like this, right? So in this case, we are given this function. So it says that the probability distribution function takes this form when x is between 1 and 4. Otherwise, it is 0. So if we plot this, and we have x here, and we have f of x here. So between 1 and 4, we basically have a curve which is x squared minus x. So 3x squared minus x. Here it will be 3c. If we put the value 1, we have 3 minus 1, which is 2. So it will be 2c. Here, to input the value 4, we have 4 square is 16 into 3 minus 48. 48 minus 4 is 44. So we have 44c. Yeah, 44c. This is here. So our function will be somewhat like this. And so this is a probability distribution function. Anywhere here, the probability is 0. Anywhere here, the probability is 0, right? So what we are doing in this case is we are given this and we are given this variable, which is c, which we need to figure out. So what we are saying is the integral, or basically the area under this whole curve from minus infinity to plus infinity, the sum or the area of under this curve is basically equal to 1, because we are talking about probabilities here. So that is what we have written here, that from minus infinity to infinity, since this is a continuous distribution, we will be taking the integral of it, right? So our integral basically gives us the area under the curve, right? So we have the pattern of the curve and we are taking the area under the curve. So this basically is the area under probability distribution function, right? So that area is 1, because the sum of all the probabilities for the continuous case will be 1, right? So that is basically what we have written here. And now what we are doing after that is, since we know that this function is 0 in most of the places, but it takes a certain form between 1 and 4. So we are basically dividing the whole region between minus infinity to plus infinity into 3 regions. So we have one region from minus infinity to 1, one from 1 to 4, and one from 4 to plus infinity, right? What we are doing here is we are basically dividing that integral into 3 parts. So we have f of x dx. Now the limit is changed from minus infinity to 1. Here it's from 1 to 4, and here it's from 4 to plus infinity. So we are basically segmenting it into 3 parts. Now we know that we are given that if the number, if x is, so uh, are you guys comfortable with like calculus? Since you said like you have non-medical, uh, like for rest of you also, like are you guys okay with calculus? Do you understand the basics of calculus and why we are taking integral, what it means and all that? Okay. So then it's easier. So what we are doing here is basically we are dividing this into 3 different parts. Here, the first part, it boils down to 0, because if x is less than 1, here in our limit, x will range from minus infinity to 1, right? So x is less than 1. Uh, yeah, x is less than 1. In this case, this will turn out to be 0. Again, when x is greater than 4, since we have this kind of operating curve here, what we have is when x is greater than 4, it's again 0, right? So this half of it again turns out to be 0. So what we are left with is the middle portion. So under the limit of 1 to 4, we are integrating f of x dx, and that is equal to 1. This you can see from the curve, because we have the curve is something like this. Then suddenly it goes somewhere like this, and then it again goes back to 0. So if you're taking the area under the curve across all the, like the whole timeline from minus infinity to infinity, you're basically talking about this area, because everywhere else the area is 0, because the line is coinciding with the x-axis, right? So what we are doing is we are just taking this integral. That is what we are doing here. So we have integration 1 to 4, limit 1 to 4, f of x dx is equal to 1. Now this f of x, we have basically substituted the function, the form of the function between 1 and 4. So we have c into 3x square minus x, that we have substituted here, c into 3x square minus x dx, right? Then this constant we can take out, and then we basically do the integration. So if you do the integration, you basically, what do you say? You have 3x square minus x dx. If you do this integration, this you can basically separate it out. So you have 3x square dx integration minus x dx integration, right? So this will be 3 into x cube by 3. So in integration, what we have is, what do you say? Integral of x raised to the power n dx is given as x to the power n plus 1 divided by n plus 1. So this is the integral, plus c if you're doing it without any limits. But if you have any limits of a and b, what you do in that case is basically you have x n plus 1 divided by n plus 1. And then basically you calculate you substitute x equal to b, and you get a value for this, and subtract that by substituting x equal to a. So that is basically, I have an empty slide right now. Okay, I'll just show it here. So if you are doing integration of x raised to power n dx, we have x power n plus 1 divided by n plus 1, right? Plus c, which is the constant term, if you don't have any limits. But if you have limits a and b, and you are integrating x n dx, what you have is x n plus 1 by n plus 1 in the limit of b to a. So this basically expands to b raised to the power n plus 1 divided by n plus 1. So you substitute the value of b in x here, and then you subtract a raised by n plus 1 divided by n plus 1. So what you have is substituting the value of a here again. So this is basically what we have done with a slightly more complex equation here. So we have 3x square minus x. So when we are integrating, we can divide it into two integrals from the subtraction sign. And here what we'll get is 3x cubed by 3 minus x squared by 2. So this 3 will cancel out. So what we have in effect is x cubed minus x squared by 2. So that is what I have written here. Doing this integration, we get x cubed minus x squared by 2 in the limits of 4 to 1. So what we have done here is, here I have substituted x equal to 4, and here I have substituted x equal to 1. And we basically take the value of this and subtract the value of this. This is basically our integration. And the rest of it is basically calculation. 4 cube is 64, 4 square is 16, divided by 2 is 8. Then 1 cube is 1, 1 by 2 is 0.5, right? So this is 56, this is 0.5. If you subtract, it's 55.5. So C is 1 by 55.5, which is 2 by 111, right? Was that clear? So all of this like comes from the simple fact that uh, the in a way you can say that the probability of all events is one. So probability of sample space. How we get 3 into 2? Where is 3 into 2?
So 3x square. How we get 3x square?
So 3x square is basically given in the equation, right? Here. So this is the value. We are integrating
Okay.
this. So that's what I was saying, that we are basically this 3x square minus x, the c is taken outside. We are integrating this. So when you integrate this, as I said here, actually, here. So we have 3x square minus x. When you're integrating this x square, you can integrate to x cubed by 3. So this cancels out, and this x integrates to x squared by 2. So we have this. And that 3x square comes from the question. So we are given this form of the equation within this bounds, right? Is that clear?
Oh, yes, sir. Okay. Thank you.
Yeah. Uh, okay. So does anyone else have any questions or doubts? I think in your assignment also you'll have something like this. So if you guys are not very comfortable with calculus, then I would suggest that just look into basic calculus, like nothing too complicated, but at least you should know, like, for example, x n dx integration, what is that? E to the power x integration, what is that? And like the different rules of integration, for example, chain rule, or like how integrals can be spread over addition or subtraction, right? For example, what we did here is basically, what do you say? This integral, we divided it into two integrals, right? So that is possible. And so just brush up on those kinds of things, because you might get a question from this in your exam where you have to make this calculation or something like this for like probability distributions, right? A lot of like probability deals with integrals, not a lot of differentials, but a bit of integrals, yeah. Anyways, yeah. So is there any other doubt or question? Yeah. Okay. So, yeah. I'll be here for 10 more minutes. If anyone has any questions or doubts, if they want to like discuss about anything that was taught in the class that was difficult to understand or something, feel free to like unmute yourselves or ask in the chat. So I'll be here till let's say 7:45. I'll just turn off my camera and yeah, just feel free to ask questions or like uh, yeah, in the chat or unmute yourself if you have any doubts. Yeah. Okay, so the ninth question. Okay, so three cards are dealt from a well shuffled deck. So what is the probability that among the cards dealt, there is exactly one king, right? So that is the question. Is there any way to identify and calculate first? So you just need to practice. So the simple thing is like if you are basically in your exam, you will have a calculator, right? So you can just use that calculator to make these calculations instead of like, since I'm doing all of these mostly by hand, and towards the end, I'm using a little bit of calculator. So I'm like trying to simplify it down as much as possible. But if you are using a calculator and it is a scientific calculator, and you arrive at, let's say, this formula, right? So you understand how this formula came to be. That why we have this many total number of possibilities and why these many possibilities are the correct possibility. That part you understood, right? Huh. So if you understand that part, then basically easier way for you to calculate would be to just input this into your calculator. So most scientific calculators will have a function to calculate C or P. So NVR and CR, they'll have functions to calculate that. I'm not sure if the NPTEL one has it, but even if it does not has this, it might have, it should have like a way to calculate factorial, right? So you can just write this equation and you can just calculate this whole number and this whole number without having to simplify. And then you just have two numbers from which you take the, what do you say, fraction. So that will make it easier. Since we are, in this case, what we are doing is we are basically doing it like I'm doing it mostly by hand. So what I'm trying to do is simplify it and then do it. But you can also just directly input everything in a calculator. Right. Is that clear? Once you like practice a few of these questions and like uh, try using the calculator, I think NPTEL somewhere would provide a link to that calculator. So try using that calculator, then you might be more comfortable with doing this fast. Sorry. For example, I think I'm not sure if this is the one that they use, but this is a calculator which you guys can try out. It has a place to calculate the factorial, so you can just write 52 factorial into whatever you have. Like, for example, if I share my screen here, you can see that you can make up things like this. So into 12 factorial to leave us here. Right, so these calculations, you can make it quicker if you use like a calculator directly instead of like simplifying. Right. Okay. So if no one else has any questions, we'll stop here today and we'll meet again next week. Someone is typing. Okay, yeah. So yeah, thanks. Thanks, guys. Also, yeah. So we'll meet again next week and we'll discuss questions related to week 5. So week 4 is done. Yeah. So I'll be uploading this session onto YouTube. If you guys want to revisit it, you can also do that. Or if any of your friends are unable to attend this session because I think today was Independence Day. So happy Independence Day, everyone also. So yeah, we you can ask them to like check it out on YouTube. Okay. Yeah, thanks for attending, and we'll meet next week, and we'll stop here today. Bye.